In this segment, I want to show you how RSA is used in practice, and in particular, I want to tell you about a standard called Public Key Cryptography Standard Number 1, PKCS 1. So I've already told you a couple of times that you should never use what's called textbook RSA. You should never directly encrypt a message using RSA because that's insecure. You always have to do something to the message before you actually apply the RSA function. We saw the ISO standard in a previous segment where what we did is we generated a random X, encrypted X using RSA, and then from this X we derived a symmetric encryption key. But that's actually not how RSA is used in practice. In practice, things work a little differently in that typically what happens is the system generates a symmetric encryption key, and then RSA is asked to encrypt the given symmetric encryption key rather than generating the symmetric key as part of RSA encryption. So in practice, as I say, what happens, the RSA system is given as input a symmetric encryption key to encrypt. For example, this could be an AES key that would be like 128 bits. And then the way this key is actually encrypted is first we take these 128 bits and we expand them into the full modulo size. For example, this would be 2048 bits. And then we apply the RSA function. And so the question is, how should this pre-processing be done? How should we expand the 128-bit AES key that was given to us into a 2048-bit value that can then be applied with RSA? And then furthermore, the question is, how do we argue that the resulting system is secure? So an old way of doing it, which is actually very widely deployed in practice, is what's called PKCS 1 version 1.5. Public Key Cryptography Standards. That's what PKCS stands for. So I want to show you how this mechanism works, and in particular I'll show you what's called PKCS 1 Mode 2. Mode 2 denotes encryption, Mode 1 denotes signatures. So here we're going to just focus on encryption. So the way PKCS 1 works is as follows. You take your message, this would be the 128-bit AES key for example, and you put it as the least significant bit of the value that you're creating. The next thing you do is you append 16 bits of 1 to it, FF, this is 16 bits of 1. And then the next thing you do is you append a random pad that actually does not contain FF anywhere inside the random pad. So this is basically something like on the order of, 1900 random bits, except that there are no FFs inside those random bits. And finally, at the very top, you put the number 02. This indicates that this plaintext has been encoded using PKCS 1 Mode 2. And then this whole value here, this whole thing that we just created, this is this 2048-bit string, is the thing that gets fed into the RSA function and is raised to the power of e modulo n. And the resulting thing is the PKCS 1 ciphertext. Now the decryptor, of course, is going to invert the RSA function. He's going to get back this blob. He's going to look at the most significant bits and he's going to say, there's a 02 in there. That means that this is PKCS 1 formatted. Since it's PKCS 1 formatted, it's going to remove those 02. It's going to remove all the random pad up until the FF. And then anything that stays beyond that is the original message, which is then used, to say, decrypt the actual body of the ciphertext. And as I said, this mechanism is extremely widely deployed. For example, it's used in HTTPS. Now, interestingly, this PKCS 1 version 1.5 was designed in the late 80s. There was really no security proof to argue that this mechanism is in fact secure. And as it turns out, as is very common when there is no security proof, it turns out that actually things break. And there's a very, very elegant attack due to Bleichenbacher back in 1998, Daniel Bleichenbacher, which shows how to attack PKCS 1 when it's used, for example, inside of HTTPS. So let's see how the attack works. So the idea is this. Suppose the attacker intercepted a certain ciphertext. So this is a PKCS 1 ciphertext. So the plaintext is encoded using PKCS 1, and then the result is fed into the RSA function, and we call the ciphertext the output of the RSA function. The attacker wants to basically decrypt the ciphertext. So let me show you abstractly what the attacker is going to do. We're going to just simplify SSL and just say that the attacker can basically send the ciphertext directly to the web server. The web server is going to try and decrypt the ciphertext using its secret key. And then what is it going to do? Well, the first thing he does after decryption, it's going to ask, is the decryption of the ciphertext PKCS1 encoded? In other words, it's going to look at the most significant bits and ask, is there a 02 in the most significant positions? If there are, it's going to continue properly decrypting and then continuing with the protocol. And if there is no 02 in those positions, it's going to announce an error. So if the most significant bits of the plaintext are 02, it's going to continue with the protocol as expected. If the most significant bits are not 02, it's going to send back an error message and tell the attacker, hey, you sent me an invalid ciphertext. Now the amazing thing is that this lets the attacker test whether the 16 most significant bits of the decryption of a given ciphertext are 02 or not. In other words, the attacker can submit whatever ciphertext he wants to the web server. The web server will invert the RSA function and then tell the attacker whether the inversion started with 02 or not. So it, in some sense, gives the attacker an oracle that lets him test whether the inversion of any ciphertext begins with 02 or not. And it turns out that's actually enough to completely decrypt any ciphertext the attacker wants. Just that little bit of information leakage, just by properties of RSA, lets the attacker completely decrypt a given ciphertext C. Well, so here's what the attacker is going to do. Well, he has a ciphertext that he wants to decrypt. So what he'll do is he'll take his ciphertext and, of course, feed that directly into the web server and ask, does it begin with a 02 or not? The next thing he's going to do is he's going to choose a random value R, and he's going to build a new ciphertext C prime, which is R to the E times C, modulo N. Now what does that do? If we pull the R into the RSA function, really what we just did is we multiplied the RSA plaintext, the PKCS1 encoding of M, we multiply that by R, and that whole thing gets raised to the power of E. Okay, so that's the effect of multiplying C by R to the E. It multiplies the plaintext by R, a value that the attacker controls. And then he's going to send C prime to the web server, and the web server is going to say, yes, this starts with 02, or no, this doesn't start with 02. So now we can abstract this problem to something more general, which you can think of as the following. So I have this number x in my head. This is the number I'm trying to get, the PKCS1 encoding of M. I'm thinking of this number x, and then what I let you do is for arbitrary r's of your choice, I will tell you whether r times x mod n starts with 02 or not. And it turns out by asking enough questions, it turns out you need about 1 million questions of this type, you can basically recover all of x. Just by learning whether r times x begins with 02 or not, by asking enough questions, you can actually recover x. So in reality, what this means is that the attacker can capture a given ciphertext. This maybe correspond to a ciphertext where the user entered a credit card number or a password, and now the attacker wants to decrypt the ciphertext. What he would do is he would send about 1 million ciphertexts like this. The web server for each ciphertext is going to respond whether the plaintext begins with 02 or not, and at the end of the attack, the attacker just walks away with the decryption of the ciphertext C. So this might seem a little magical to you. How are you able to, just from learning whether the most significant bits are 02 or not, how are you able to recover the entire plaintext? So let me show you a simple example of this. I'll call this baby ablation blocker just to kind of get the idea across for how this attack might work. So imagine that the attacker is able to send the ciphertext C. The web server is going to use his secret key to decrypt, but let's suppose that instead of checking for a 02 or not, all the web server does is he asks, is the most significant bit 1 or not? If the most significant bit is 1, the web server says yes. If the most significant bit is not 1, the web server says no. Moreover, to simplify things, let's assume that the RSA modulus n is a power of 2. So n is equal to 2 to the little n. Of course, this is not a valid RSA modulus. An RSA modulus needs to be a product of two distinct primes. But again, just to keep things simple, let's pretend for a second that n is actually a power of 2. So now you realize that by sending the ciphertext C over to the web server, the adversary just learned the most significant bits of the plaintext X. Basically, the server's behavior completely reveals what the most significant bit is. Now what the attacker can do is he can multiply the ciphertext by 2 to the E. Now multiplying by 2 to the E has the effect of multiplying the plaintext X by 2. Simply multiplying X by 2. And because we're working mod 2 to the N, multiplying by 2 basically means shift left. Okay, so now when we shift left, in fact, we get to learn now the most significant bits of 2x, which is really the second most significant bit of x. Okay, so again, the most significant bit of 2x, basically we shift x to the left and we reduce modulo n. So now the most significant bit of 2x modulo n is basically the second most significant bit of x. So now we learned another bit of x. And now we're going to repeat this again. We're going to query at 4 to the e times c. That corresponds to querying at 4x to the power of e. Querying at 4x basically reveals the most significant bit of 4x mod n. 4x multiplying by 4 corresponds to shifting by 2 bits, which means that now we get to learn the third most significant bit of x. And we repeat this again and again and again for different multiples of c, and you can see that after just a few queries, about 1,000 or 2,000 queries, we'll recover all of x. The reason Fleischerbacher needed about 1,000,000 queries is because he wasn't testing for 1, he was actually testing for 0, 2, or not 0, 2, and that basically means that he needs, instead of 2,000 queries, he needs actually 1,000,000 queries, but that's still enough to recover all of the plaintext x. Okay, so I hope this explains why this attack is possible, why just this little bit of information about the most significant bits of the RSA inverse is enough to completely decrypt RSA. So the bottom line here is that PKCS1, as implemented in web servers up until this attack was discovered, was basically insecure because the attacker could essentially decrypt any ciphertext he wants just by issuing enough queries to the web server. So how do we defend against this attack? Well, so in the SSL community basically wanted the minimum change to their code that would prevent this attack from working. And so if you look at the RFC, what they propose is the following. Well, there's a lot of text here, but basically what they propose is to say that if after you apply the RSA decryption, you get a plaintext that's not PKCS1 encoded. In other words, it doesn't start with 0, 2. What you're supposed to do is basically choose some random string R and just pretend that the plaintext is this random string R and continue as if nothing happened. And of course, the protocol will fail later on. So to be concrete, you see if the PKCS1 encoding is not correct, what you would do is you would just say the pre-master secret is this random string R that we just picked out of thin air, and let's continue the protocol. And of course, the session setup will fail because the client and the server will end up agreeing on different keys, and that will cause the session to terminate. So we actually don't tell the attacker whether the plaintext begins with 0, 2 or not. All we do is we just pretend that the plaintext is some random value. So this was a minor code change to many web servers, and it was fairly easy to get deployed. And in fact, most web servers out there today implement this version of PKCS1. However, this kind of raises the question of whether PKCS1 should be changed altogether so that we actually are able to prove chosen ciphertext security. And that brings us to a different way of doing encryption using RSA, which is called optimal asymmetric encryption padding, OAEP. And in fact, the PKCS standard was updated, and PKCS1 version 2.0 actually has support for OAEP, which is a better way of doing RSA encryption. So let me explain how OAEP works. So OAEP is due to Belara and Rogaway back in 1994. And the way OAEP works is as follows. So you take your message that you want to encrypt. This, for example, could be the 128-bit AES key. And then the first thing you do is you append a short pad to it. So in this case, you put a 0, 1 at the beginning, and then you append a whole bunch of zeros. How many zeros is actually depends on the standard, but let's suppose that there are like 128 zeros in here. And then you also choose a random value so that this whole string is as big as your RSA modulus. So let's just say this is 2047 bits. Now, before you apply the RSA function, you first of all take the random value that you chose and you feed it into a hash function. This hash function produces a value that's as big as the left-hand side of your encoding. You XOR the outputs. You feed the result into another hash function, which we call G. You XOR that with a random value. And then finally, you get these two values that you can concatenate together. Okay, so you concatenate the left side and the right side. That gives you something that, say, is 2047 bits long. And that's the thing that you apply the RSA function to. And the result is the RSA encryption. Now, there's a theorem that was proved in 2001 due to Fujisaki, Okamoto, Poinchevel, and Stern that shows that, in fact, if all you do is you assume that the RSA function is a trapdoor permutation, a secure trapdoor permutation, then, in fact, this mode of encrypting using RSA is, in fact, chosen ciphertext secure. But we have to assume that the functions h and g are kind of ideal hash functions. And as I said, these are called random oracles. Basically, we assume that h and g are just random functions from their domain to their range. In practice, of course, when OAEP is implemented, people just use SHA-256, say, for h and g. Why is this called optimal asymmetric encryption padding? Why is this O? Why does it stand for optimal? Well, the reason is if you look at the ciphertext, you notice that the ciphertext is basically as short as it can be. The ciphertext is exactly the length of one RSA output. There are no trailing values that are appended to the ciphertext. Whereas, for example, the ISO standard, if you remember, even if you had to encrypt a very short message, what you would have to do is you would have to encrypt X using RSA, and then append to that X the encryption of the short message under the symmetric encryption system. So even if you have just to encrypt a 128-bit AES key, with the ISO standard you would get one RSA output plus a symmetric cipher. Whereas with OOEP, you just get one RSA output and nothing else. So in that sense, it's optimal. Optimal in terms of the length of the ciphertext. Interestingly, this theorem here really relied on properties of RSA, and in fact, this theorem is known to be false if you use a general trapdoor permutation, some other permutation that doesn't have the algebraic properties of RSA. So that left this question of, if we have a general trapdoor permutation, what is the correct way to do OOEP? And it turns out there's a minor modification to OOEP which makes the result more general. This is a result due to Shoup back in 2001. Just shows that if you give me a general trapdoor permutation F, it turns out if you replace the fixed pad that's used in OOEP by a hash function, this hash function W, which happens to be a hash function of the message M and the randomness R that you're encrypting with, and then during decryption, you actually check that this hash function value is correct. So when you decrypt, you actually check that W of MR is really what's written in this position in the plaintext. If you do that, then basically this OEP called OEP plus is in fact CCA secure. It's chosen ciphertext secure for any trapdoor permutation. You don't have to rely on specific properties of RSA. There's another result called simple asymmetric encryption padding, SAEP+, which basically says that if you are going to rely on properties of RSA, then in particular with RSA when the public exponent is equal to 3, it turns out you actually don't need a second stage of encryption. The simple padding scheme here, again using the function W, is actually already enough to guarantee chosen ciphertext security. So these are variants of OEP, but they're not really used. I just wanted to mention, and so that you know they exist. These are not really used. Mainly OEP has been standardized, is what's used, although again in reality the most common application of RSA for public encryption is in fact this PKCS1 that's standardized in the HTTPS RFC. So just to make sure it's clear in your mind how decryption actually works, let me ask you, how would you decrypt an SAEP ciphertext CT? So here you're given the ciphertext CT here, and the question is which of these three methods is the correct way of decrypting the ciphertext? So the correct answer is the first one, and let's see why. Well, given the ciphertext, the first thing we would need to do is apply the RSA inverse function to ciphertext, and that would give us the RSA plaintext, which happens to be in this case X and R. So we get these X and R here. The next thing we need to do is we need to hash R using the function H and XOR the result with X, and that would give us M and WM comma R. And the last thing we need to do is to make sure that the pad WMR is correct. So we check that in fact W is equal to WMR. And if so, we output M, and if not, we output bottom to say that the ciphertext is invalid and the decryption algorithm rejects it. And by the way, I'd like to emphasize that this checking of the pad during decryption is crucial in all these schemes that we just saw. So for example, in both OEP plus and SAEP plus, it's during decryption, it's very important to check that the pad is in fact correct, so that the value of W that you get here during encryption really is the hash under capital W of M and R. And similarly in OEP, it's very important to check that during decryption, in fact, the value of the pad is the constant 010000000. And of course, if it happens to be not 01000, then you output bottom and you say the ciphertext is invalid. The last thing I want to point out is that actually implementing OEP can be quite tricky, and let's see why. So suppose you have you write an OEP decryption routine that takes the ciphertext as input. The first thing you would do is you would apply the RSA inverse function to the ciphertext, and you would say, well, you expect to get an n-bit value out, 2047 bits in the case of a 2048-bit RSA modulus, and if you get something that's bigger than 2 to the 2047, you say reject. We say error equals 1, and we go to exit. The next thing we're going to do is we're going to check whether the pad is in fact the correct pad. And again, if the pad is not the correct pad, then again, we're going to reject and go to exit. The problem with this implementation is, well, by now I hope you kind of guessed it, is that it's vulnerable to a timing attack, right? So essentially by leaking timing information, the attacker can now figure out what caused the error. Was there an error because the RSA decryption happened to be too big, or was there an error because the pad happened to be too large? And if the attacker can distinguish these two errors, say by timing, then it turns out, similar to the Blasenbacher attack, it's possible to completely decrypt any ciphertext of your choice. Just that very, very, very small leak of information would completely allow the attacker to decrypt completely any ciphertext he wants to. So this shows that even if you implement the mathematics of OEP decryption correctly, you can very easily mess up and open yourself up to a timing attack, which would make your implementation completely insecure. So as usual, the lesson is don't implement crypto yourself. In particular, RSA OEP is particularly dangerous to implement yourself. Just use one of the standard libraries. For example, OpenSSL has an OEP implementation. And of course, what they do is they're very careful to make sure that the running time of OEP decrypt is always the same, no matter what causes the error. Okay, so we'll stop here, and then in the next segment, we'll talk about the security of the RSA trapdoor permutation.